Hello, everyone. Welcome to the United States Geological Survey Public Lecture Series. Thank you for joining us this evening and at our new start time of 6 p.m. Pacific Time. We're hoping this will give our Central and Eastern states folks a better opportunity to join us live. My name is Christy Ryan, and I will be your host and moderator this evening. Before I introduce our speaker, I just have a few announcements to make, and hopefully this will give others out there in virtual world a few extra minutes to get logged in. First, I want to give you a heads up on our lecture for next month that we have scheduled. This one will be on May 26th, and we will have Paul Young, Director of the USGS National Civil Application Center, and the title of his talk will be Using Military Remote Sensing Technologies to Support Federal Civil Agency Science, Sunk Cost Well Spent. So we hope you'll join us next month as well. And at the end of the lecture, I will provide information on how to join our mailing list, so you'll be in the know on all future talks. So the next part of the announcements is I want to give you some tips on this Teams platform in case you're new to our lecture series. If you're watching this on a desktop computer and need to turn on closed captioning, go ahead and look at the bottom right-hand corner of your screen for the closed caption icon. Another feature we want to direct your attention to is the question and answer panel, and that can be opened by clicking the question mark icon in the upper right-hand corner of your screen. At the end of the lecture, we will have a Q&A session with our speaker, and this is a panel where you're going to want to submit your questions for him. And just in advance, just understand we may not have time to get to everyone's question, but we're going to do our best. So now let's get started with our lecture for this evening. Tonight we have the pleasure of welcoming Justin Welty. Justin is a biologist and ecologist with the USGS Forest and Rangeland Ecosystem Science Center. Since 2008, Justin has specialized in spatial data programming, data analysis, database design, website design, and general scripting. He's worked to create and maintain multiple big data datasets that contribute to both research and management decisions across the West, including the USGS Combined Wildland Fire Dataset, Land Treatment Digital Library, and Conservation Efforts Database. In his free time, Justin enjoys being a husband and father to his 2 children, as well as biking, nature photography, and working on his house, yard, and garden. So without further ado, let's all give a warm virtual welcome to Justin. Justin, the floor is all yours.
Thank you. And thank you for that introduction. I also want to thank everyone out there for joining me. So I want to jump right in with a confession. I love big, complex, long-term scientific data sets. At the beginning of this talk, you may find yourself asking why we need long-term data on wildlands, areas with minimal human interaction. Why would knowing where a fire burned or a land treatment occurred 20, 50, or even 100 years ago even matter? If I do my job right, by the end of this talk, I'm hopeful you will have a better appreciation for long-term data sets, why we need them, and the amazing things we can do once we collect them. Whether we realize it or not, knowing about our past is critically important. There's a quote out there by George Santayana, but just like everything else I'm going to talk about tonight, getting the details and the context right matter. That's not actually his name. It's the simplified English version of it. His real name is Jorge Agustin Nicolas Ruiz de Santayana y Borras, and in 1905 he published his Reason and Common Sense of his 4-part examination, The Life of Reason, and produced a famous quote that is just as often misquoted as it is quoted correctly, but it's very pertinent to our discussion this evening, and it's important to get it right. Progress, far from consisting in change, depends on retentiveness. When change is absolute, there remains no being to improve and no direction is set for possible improvement. And when experience is not retained, infancy is perpetual. Those who cannot remember the past are condemned to repeat it. As scientists, we can use historical data to help explain past and current patterns and model what the future might look like. Humans rely on correctly captured historical data all the time in our daily lives, whether we realize it or not. So what is a long-term data set? Put simply, it is any data set that captures data on a subject over a period of time. Let's look at an example that many of us can relate to, digging in a residential area. This past December, the 63-year-old water main that supplies water to my house started leaking. The excavation crew dug a 16-inch wide by 5-foot deep by 20-foot long trench in our front yard to lay a new line for us. Digging a massive trench through someone's property is not without risk. They had to miss the natural gas line, which thanks to city records, we know is under the raised flower beds. They wanted to miss the old water main lines so we could keep our water running as long as possible throughout the construction, and the city records placed it right beside where they dug. Additionally, there could be other buried pipes, electrical wires, and who knows what all else, including sprinkler lines, which they cut through in multiple locations. That's the whole reason for the call before you dig commercials, and the reason they capture all this data. You never know what you might hit if you just start digging. Not knowing our past can have unintended and even dangerous consequences. That's one example of a long-term data set, but what about in the scientific world? Scientifically speaking, I would define long-term data as any data set that captures data in enough detail and at a time period long enough to identify a pattern, explain a trend, or answer the question asked. There are many examples of long-term data sets in science, but one many of you likely use every day without even realizing it is the long-term forecast. Everyone relies on the extended forecast to plan trips or even decide what they're going to wear. This is a past extended forecast for my home city of Boise, Idaho, and based on what it said about that week, I wasn't going to be working in my garden on Tuesday, and I was really looking forward to Friday. So how does something like this work? Well, meteorologists input millions of past weather data records as well as current conditions into a supercomputer. That supercomputer takes the current conditions and compares them to similar conditions in the past in order to predict what the future is going to be like. Without those past records for comparison, you could feed the computer as much current data as you want, and it would have no idea what the forecast for the next week would look like. By now, hopefully I've established that long-term data are important, not only for scientists, but for everyone. Let's look at some other examples and demonstrate how the quality of the data set and the time period it covers are often related. Basically, the length and the quality of a long-term data set comes back to the question you are trying to answer. Scientists have a general understanding of the history of the Earth itself. From its formation 4.56 billion years ago to today, the archaeological record allows scientists to determine the general time period when major events occurred, when the Earth first formed, when life first appeared, when oxygen levels began to rise in our atmosphere. Fun fact, billions of years ago, our atmosphere had basically no oxygen in it. When not a lot happened for a billion years, and when animals first appeared. However, these events are not measured in days or even years. If I were to ask you what the weather was like where you live the day the asteroid that led to the extinction of nearly all dinosaur species hit the Earth 66 million years ago, no one has any idea. At best, we have a basic idea of the climate for that general time period. We have a better idea of what has happened since the written history of humans began approximately 5,000 years ago, and can get many events down to the year, month, and even day, especially as the time period approaches the present. However, if I were to ask you that same weather question the year the Magna Carta Libertarum was written in 1215, you would still not be able to get any closer to the exact weather in your area on a day in that year than you could 66 million years ago. However, if I were to ask you what the weather was like in the place and time of your birth, now that you might be able to get pretty close. That's because over the last century, we have placed more and more weather stations across the world that record temperature and precipitation daily. Therefore, long-term data should be considered a function of the question you are trying to answer, consisting of the time period of interest and the quality of data in that time period. You might ask why we need long-term data to view patterns and trends. Now, patterns and trends in nature, if viewed in the short term, can look convincing, but can often be deceiving. In 2017, David Pilliot, Robert Arkell, and I published a paper looking at how precipitation and vegetation conditions drove wildfire trends in the Great Basin. The Great Basin is a cold desert located in Nevada and parts of the surrounding states shown in the dark black outline. It is primarily composed of shrublands and grasslands with forests present only in the higher mountain elevations. We utilized a 25-year continuous long-term vegetation monitoring dataset captured within the Morley-Nelson Snake River Birds of Prey National Conservation Area, seen here in the red polygon, to look at how annual precipitation drives vegetation changes. In other words, we were looking at whether more rain would lead to more grasses and flowers. And once we established we could predict vegetation cover using precipitation alone, we looked at how precipitation amounts could predict wildfires in this region since 1980. So why do we need 35 years worth of precipitation and fire data to identify the pattern? Here's another figure from that same paper, except I've grayed out all the data in the middle. On the x-axis at the bottom of this figure, we have water year from 1980 to 2014, or 35 years worth of data. And water year, unlike the calendar year, actually runs from October to September. The primary y-axis on the left side shows the total precipitation, shown as various colors of blue bars, for different seasons of that water year. So we've got October to March in dark blue, April to June in light blue, and July to September in very light blue. And it's all measured in millimeters. The secondary y-axis on the right side shows the number of hectares burned in the Great Basin times 1,000. And it's shown by that red line you see at the bottom of 1980. To provide some additional context for you, I'm adding a blue line on the primary y-axis here at 269 millimeters. That was the average precipitation in the Great Basin for this time period. And you can see in 1980, our precipitation is well above average. I'll add a red line on the secondary y-axis at 370 hectares, meaning about 370,000 hectares burned in wildfires in the Great Basin on average every year in our time period. To put that in perspective, that means an area larger than the state of Delaware has burned every single year in the Great Basin from 1980 to 2014. And our area burned in 1980, you can see with that red line, is well below average. So let's open up some short-term 5-year windows and see what the data is telling us, starting with 1980 to 1984. So in this period, 4 of the first 5 years are above average precipitation and well below average number of fires. And that makes sense. If it rains a lot, a fire is going to have trouble getting going because all the fuel is wet and green. Well, let's open up a second window from 1987 to 1991, while leaving the first window up for comparison. In this time period, the Great Basin gets consistently around 250 millimeters of precipitation a year, right at or just below average, with almost no variation, and the hectares burned is still well below average. This 5-year window is very different from our first 5-year window. However, this pattern also makes sense. If it's dry in a desert, not that many plants can grow, and the ones that do aren't very big. It's hard for a fire to get going if there isn't a lot of fuel to burn. So wait a minute. Now I'm saying if it's wet, it doesn't burn, and if it's dry, it doesn't burn. To get to that average fire line of 370,000 hectares, there must be more hectares burned than average in some years. So let's open up a third window. This time from 1997 to 2001, and we see precipitation start above average in the first 2 years, but drop below average in the last 2, and hectares burned spikes above average right in the middle. Again, this is a very different pattern than our first 2 windows. However, this might be the answer. Do we need precipitation to go from high to low to have a high fire year? Maybe. But if we just looked at one of the other 2 windows, we would have never come to that conclusion. And even here, we don't have enough information to draw any conclusions about long-term trends. By stepping back and viewing the precipitation patterns over a long period of time, in this case 35 years, we can finally see the pattern in the Great Basin. The Great Basin is very cyclical. In general, we cycle through 1 to 3 years of above average precipitation, followed by up to 6 years of average or below average precipitation. This is a desert after all. Let's look at the 5 spikes where the area burned is above average, signifying very severe fire years. What do they all have in common? All the spikes are preceded by 1 or more years of above average precipitation. But why would getting lots of rain drive fire? It turns out rain makes plants grow. Who knew, right? But in the desert that is the Great Basin, extra rain really makes grasses and flowers grow much larger and in much higher quantities. Desert plants are adapted to dry conditions, but absolutely thrive when the rain does come. Those grasses and flowers die back in the winter to form dead plant material on the ground, or what we call litter, and new shoots sprout again in the spring. It turns out this litter can persist for up to 3 years due to the dry desert environment. So basically, wet years create a bunch of dry, fine kindling in subsequent years. But as long as it stays wet, that kindling isn't very flammable. When the area cycles back to an average or dry year, The Great Basin has essentially built up a store of highly flammable litter just waiting to go off, and this results in very severe fire years. Fortunately, as things continue to stay dry, this litter breaks down in a couple of years and isn't replaced in such large quantities, so the fire threat drops until the cycle repeats. Without long-term weather, vegetation, and fire data sets to look at this pattern across space and time, we would have never been able to statistically validate and demonstrate the highly predictable nature of this pattern. Now that we have a definition of a long-term data set and an example of what we can do with them, I want to turn our attention to long-term data sets that I have been working on: the Land Treatment Digital Library and the Combined Wildland Fire Dataset. Let's spend some time talking about why we developed each dataset, why it's needed, how it's being used, and wrap up with how we are working to make these two datasets more publicly accessible so that anyone can utilize the data to view patterns and trends and answer their own questions. Let's start with the Land Treatment Digital Library, or LTDL, and begin by defining what a land treatment is. A land treatment can be thought of as any on-the-ground soil or vegetation manipulation designed to meet a specific objective. Some examples include things you might do in your own yard, just on a much larger scale in wildlands. Seeding an area to restore native grasses, flowers, shrubs, or trees. Conducting a prescribed fire to reduce the threat of a dangerous wildfire. Spraying herbicide to kill unwanted plants and weeds. Or fencing an area to protect it from animals that might damage the soil or vegetation. One agency that conducts thousands of land treatments every year throughout the western United States is the Bureau of Land Management, or BLM. The BLM manages over 38,000 square miles of land, shown here in blue, almost all of it in the contiguous western United States and Alaska. The BLM is charged with managing the land for multiple uses, including mineral, gas, and oil development, recreation, grazing, and maintaining native healthy landscapes. The BLM manages huge swaths of rangeland, mostly consisting of grasses and shrubs, but also some forests. Lately, the BLM has been constantly battling threats to the ecosystems they manage, and the biggest threats tend to be wildfires and invasive species. Fires consume the native grasses and shrubs, and after the fires, invasive non-native species often move in and make the area even more fire-prone and create a feedback loop where successive fire makes invasion by even more non-natives more likely. These cycles destroy native vegetation and create an ecosystem that is both less hospitable to other native life forms and more likely to burn again in the future. To combat these and other threats, the BLM conducts many different land treatments. We need to know where these treatments have been conducted so we can see what has been done, monitor for effectiveness of these treatments, determine what has worked and what hasn't, and be better prepared to respond and adjust to outcomes of future treatments, a concept known as adaptive management. Adaptive management occurs when a treatment is planned and implemented, its effectiveness is monitored, and all that information is archived so that it can be used for future treatment planning. The only way to do this effectively at a landscape level is by centralizing and standardizing the data. Until 2008, when I first started the LTDL, documentation on these BLM land treatments were stored only in file cabinets, local hard drives, internal servers and databases, or even just in someone's mind. This decentralized storage method can inhibit research, knowledge sharing, and in worst case scenarios can lead to a loss of data. A desire to capture, centralize, and store that information, in other words, to archive it, was one of the main drivers behind the creation of the LTDL. So what is the LTDL? It's a data repository or library designed to capture detailed information on land treatments. We don't call it a database because it stores so much more than just data. We capture the spatial location the treatment took place, supporting documentation like plans and reports, and hundreds of tabular data fields. For some treatments, we can tell you exactly where a treatment took place, when the treatment took place, what species were seeded, or what chemicals and in what amounts were used to spray for weeds. Currently, we capture information on BLM activities in the contiguous Western US only, as that is what the BLM has funded us to do. Now, once the utility of the LTDL was proven, interest in this product has exploded. Today, crews still travel to over 100 BLM field offices across the West to collect or scan the data and manually enter into the LTDL. There's a reason the project still is ongoing to this day. Capturing and recording information on thousands of land treatments every year is no small task, even for a group of individuals. However, our crews have worked hard over the years, And currently we have nearly 60,000 treatments in the LTDL, shown here in those little red polygons, and they reported treating over 57 million acres of land. Now, many of those acres are multiple treatments being conducted over the same area, and we don't actually have polygon areas for all the information in the LTDL. Still, our uniquely treated polygon areas cover over 24 million acres of land, or larger than the state of Maryland. It's a phenomenal amount of data. Let's take a look at some of the highlights in the LTDL, as I think this is truly an impressive data set of the BLM's treatment history. The first year we have a record of a treatment is actually 1917. That is before the BLM even existed. The most recent is 2022. We have over 15,000 seeding treatments shown here on the map, including 3,600 aerial seedings where they're dropping seed from a plane or helicopter, over 4,000 drill seedings where they're using a drill to stick the seed under the soil, and 6,400 other seeding types. While you're looking at these maps, I want you to see if you can identify patterns and determine which areas receive the most treatments. Now, if you look at the legend here, you notice that we have polygons, lines, and points to represent our seedings. Now, point seeding doesn't make any sense. You're not going to drop seed in a single spot on the ground. But when it comes to long-term data sets, or any data set for that matter, context matters. You need to understand the reasoning behind what you are seeing. In this case, we don't have exact spatial locations for all our treatments. Some of that has been lost. So we place an approximate point on the ground to indicate that a treatment took place somewhere in the area. Some data, even if it isn't perfect, is still better than no data, as long as you qualify and understand what you're looking at. The LTDL has a lot more than just seedings. We have over 6,700 prescribed burns, over 3,800 soil disturbances like plowing or disking, over 5,400 timber harvests, and over 5,500 vegetation disturbances like mowing or hand cutting. When you stack all those treatments up on a map, the results are impressive. But again, context matters. The seedings and prescribed fires in green and orange respectively are underneath the other treatments on this map. If I were to just show you this map, you might come away thinking the BLM does very few seedings or burnings. However, I could tell a completely different story if I put those seedings and prescribed burns on top. Now it looks like the BLM does almost nothing but seedings. So what can long-term data sets teach us? First off, context matters. With enough data, by showing you bits and pieces, I could tell you any story I wanted. Understanding the details behind the data, how it was collected, and what the caveats are can help you really understand and appreciate the data you are looking at. So let's look at the LTDL data another way. Here's a graph showing a count of all treatments in the LTDL. Completion year of the treatment is on the x-axis at the bottom, and the number of treatments is on the y-axis on the left. One of the many context-specific fields we have in the LTDL indicates whether we have confirmation the treatment took place. Is it a confirmed treatment or planned unknown implementation treatment? We know from talking to the BLM that planned treatments were often conducted even if we can't confirm it. So we didn't want to get rid of the data. We just wanted to provide additional context to that data. If I want to look at the data set of only those treatments I know took place, I can filter on that data. In this case, it is all the red shaded area, which comprises the majority of the treatments. We have qualifiers like this all over the LTDL, allowing researchers to drill down to the very best data if needed. Okay, let's switch gears now and talk wildland fires. If you pay attention to the news or live in a fire-prone area, you know that fires in general, and particularly wildfires, have become a very hot topic. Wildfires are often mischaracterized in popular media, and while some fires are incredibly destructive and deadly, fire is also a normal, even essential part of many ecosystems. Therefore, understanding what has burned, where it has burned, and how often it burns is critical to our understanding of fire processes. There are two different kinds of wildland fire in a natural landscape. A wildfire is an unintentional, potentially out-of-control fire started either naturally or by humans that burns over woodlands, shrublands, grasslands, or other native natural vegetation. While these fires make national headlines for their numbers, size, and destructive capabilities, particularly when these fires burn through and destroy houses, neighborhoods, or even whole towns, they are, again, an essential part of many ecosystems. A prescribed fire, on the other hand, is an intentional, controlled fire started by humans that burns over those same wild vegetation types, but is designed to consume these natural fuels when the fire is less likely to get out of control and the fire is designed to be less severe. Now, wildfires typically burn from summer to early fall or in the dry season when the dry vegetation and weather creates conditions ideal for fire spread. Prescribed burns are often conducted in the fall, winter, or spring, or when conditions are wetter. The fire is less intense and cannot be spread easily. Prescribed fires, if you remember, are actually a type of land treatment that we also capture in the LTDL. Given the national interest in fires, particularly wildfires, there's an intense interest in studying fires, determining fire trends, and determining what areas are most at risk for severe wildfires. Because of this interest, it makes sense that there are a lot of fire data sets out there. In fact, last I checked, there are over 50 different ones. The sheer number of data sets out there presents its own set of problems. These data sets can cover different areas and time periods, include one or both types of wildland fire, have multiple different polygon shapes for the same fire, have lots or very little information about each fire, and finally, the fire location may be represented by a centroid point or contain the actual polygon of the area burned. Without carefully looking into all that important context, you could easily use the wrong dataset and come to incorrect conclusions. Or you could use the dataset correctly, but come to different conclusions than someone else who used a different dataset correctly. So why did we create one and what did we do differently? Well, we created one because all these inconsistencies drove us to a need for a consistent single wildfire dataset. So first, we're working with a team of fire experts from a range of agencies and other groups. This is helping us really dive into that context I keep coming back to, so we have a better understanding of the context behind the different fire datasets that are out there. Michelle Jeffries and I, who create the Combined Wildland Fire Dataset, are not fire experts. By working with this diverse group, we know what's important, what data is more questionable, and can better address fire questions or point individuals to the right people or dataset when we need to. Next, we have scoured the internet looking for publicly available datasets to provide a more comprehensive picture of fire than exists elsewhere, and we continue to look for and add additional datasets with each year's updated release. We take all these datasets, run them through an extensive quality control process, and merge them into the combined dataset. Now, 3 of our datasets didn't merge with the rest. That's because these polygons didn't exist on the internet, at least in a digital map form. Fire data before the use of satellite imagery to detect fires in 1984 is notoriously incomplete. We took the paper maps of these fires and sketched the polygons out on a digital map to produce these fire boundaries. As far as we are aware, we have the only digital spatial polygon copies of these fires. And some of these fires are considered large even by today's standards. For anyone interested, I encourage you to look up the Great Fire of 1910 in Idaho, Montana, and Oregon. I believe the URL is being posted in the chat right now. This thing was monstrous, burning more than 3 million acres, destructive and deadly, creating its own weather with hurricane-force winds, flames flying hundreds of feet into the air, and producing fire tornadoes that sucked up burning trees, roots and all, flinging them far from the original fire and sparking new fires. It must have been an absolutely terrifying ordeal, with one person who survived referring to it as a red demon from hell. Now, currently, we are working to expand this digitization of old paper fire data maps to try to capture more of the fire history of this country and have undergraduate JS student volunteers working to digitize many more boundaries. Now, I'm not going to go into tons of detail here, but essentially we have worked hard to eliminate many of the errors present in other datasets and provide additional quality controls and context to create a comprehensive wildland fire dataset that includes fire perimeters from the late 1800s, where they're available, through 2020, with plans to update and add to the dataset every year. The fire dataset, like the LTDL, has quality control fields that allow users to filter out more questionable data and provides an analysis-ready dataset for users. The need for this type of dataset was demonstrated in 2020, when even with all the other datasets out there, the 2019 release of this dataset was downloaded over 8,000 times in its first year. Our latest release has nearly 100,000 wildfires and over 36,000 prescribed fires. And even on a scale this grand, you can start to see patterns. Most of the wildfires occur in the contiguous western US and Alaska, while a lot of the prescribed fires occur in the southeast in Kansas. Let's zoom into the West and show only wildfires and color code them so the earliest fires through the 1960s are in purples and blues. Fires from the 60s through the 90s are in teal and yellow, and fires from the 90s to present are oranges and reds. Just by looking at the data, we can begin to see patterns in terms of what areas burn the most. You can also see where fires have burned in the past, with little recent fire activity like northern Idaho and northwest Montana, for example. While just the final dataset provides valuable information, Michelle and I didn't want to just provide users with the dataset. Fire is an extremely complex issue, as multiple fires can burn irregularly over the same area. We wanted to provide additional information to help users better explore the data. And so I'm going to zoom into southwest Idaho here. This is an area with many fires and multiple repeat burns. So we provide additional contextual information that includes Excel data on errors and inconsistencies in the dataset, as well as summary visual data that displays things like this, the count of wildfires you can see here. And in southwest Idaho, multiple areas have 3 or more fires impacting the same area, represented by light green, orange, and dark red colors. This is a tremendous amount of fire that's not easily visible using just the polygon dataset, and it can have extremely detrimental effects on the landscapes where they burn. So we've got 2 complex long-term datasets that can be used for science, research, resource management, and general information for those interested. The next step is to get them out to the individuals who need them. We release both of these datasets to the general public so that anyone can download and look at them. These datasets come with full metadata or data about the data so that we can provide that additional context and give users more information about the datasets. For anyone interested, these links will be posted in the chat and available again at the end of the talk. In addition, the LTDL has a website that users can access. And again, for the LTDL, we actually respond to specific custom data requests for approved use cases where we provide the user exactly what they are looking for and work with them to provide that additional context so they know how to interpret and work with the data appropriately. Over the years, we have responded to over 100 individual data requests from multiple agencies and groups, and as this figure demonstrates, those requests continue to increase. The LTDL in particular, but also the Wildland Fire Dataset, have led to dozens of research projects and peer-reviewed publications. We are literally enabling science on a temporal and spatial scale that wasn't possible before these datasets existed. Since this is a public lecture, and it's likely some of you are not scientists, I'm sure you're not caught up on all the latest scientific articles. So let's go into each one of these in detail. Kidding. However, I do want to highlight a few of the coolest details from 2 of them. Let's start with this paper looking at 75 years of vegetation treatments in the Great Basin. Again, to orient everyone, the Great Basin is centered on Nevada and includes parts of the surrounding states and is a hotspot for BLM treatment activity, particularly in the northern and central Great Basin. In this paper, we used the LTDL to analyze how patterns and trends in BLM treatments changed over time, basically asking the question, how has the BLM changed its treatment practices over the decades in the Great Basin? In this figure, we have treatment year on the x-axis and a count of post-wildfire treatments in black and non-wildfire treatments in gray on the y-axis. What's fascinating is that you can see how legislation passed by Congress impacts the BLM's work at points 1 and 2, with the National Environmental Policy Act of 1969 and the Federal Land and Management Policy Act of 1976. At both of these points, we see a dramatic drop in the number of treatments conducted, as the BLM was required to adjust to new paperwork and policy requirements. At point 3, we actually see the opposite effect. It's a huge increase in fires in the Great Basin and other areas in the late 1990s and 2000s, and subsequent surge in treatments you can see happen right before point 3. This surge in fires led to the National Fire Plan in 2001, outlining a new approach to actively respond to severe wildland fires. In the second paper, Protecting Restoration Investments from the Cheatgrass Fire Cycle and Sagebrush Steppe, we utilized both the LTDL and the Wildland Fire Dataset to ask the question, how often are seeding treatments reburning in a high priority area? The BLM has invested millions of dollars to stabilize and restore burned areas after a fire, as well as maintain the native habitat that remains unburned. They are planning on putting up a network of fuel breaks or long skinny treatments designed to prevent fire spread along a huge network in the highlighted area here on the map. As they implement these fuel breaks, we wanted to look at how much and where their previous treatments have reburned to date. In this figure, we see year of the seeding on the x-axis and area in square kilometers on the primary y-axis on the left side. The yellow bars represent seeding treatments in that year that have subsequently burned, while the blue bars represent seedings that had not burned as of 2019. The secondary y-axis on the right shows the percent of seedings that have subsequently reburned in that year and is represented by the gray line here. Not surprisingly, the more recent a seeding is, the less likely it is to burn. This makes sense as more recent seedings simply haven't been around long enough to have a high chance of being consumed in a fire. It's also concerning because the longer these recent seedings continue to be around, the more likely they are to burn. We found that about 75% of the BLM seedings have remained unburned, and also found there are geographic differences in terms of which seedings were most likely to burn. We hope our research helps the BLM place their fuel breaks for maximum effectiveness to help protect their seeding investments and the native habitat that remains. Now, all this is great for scientists who have the time and experience to really dive into the data and study the details. However, these data can still be useful and of interest to resource managers and the general public. We just need a way to deliver it to people like you in a way that doesn't require expensive software, lots of time, and plenty of experience in data analysis. To do this, we are developing decision support tools that allow anyone with an internet connection to access these data. Let's start, as I have been throughout this presentation, with the LTDL's decision support tool, the Land Treatment Exploration Tool, or LTET. The LTET is a publicly accessible tool that allows users to draw a polygon on wildlands and get information about that land area as well as that land's history. While it's specifically designed to help users plan treatments on wildlands, it's a fully interactive tool that anyone can use to learn more about the wild areas around them. Again, this is based on the LTDL, so it is focused on the western contiguous US. However, the tool has limited functionality in the eastern US as well. So what is the LTET? Well, first, it's an interactive web map with over 60 different layers you can turn on and off and identify features about your site, as I'm demonstrating here with shrub cover. It provides you with a treatment history from the LTDL, so you can see where, how many, and what types of BLM land treatments have occurred in the area. It includes a fire history, allowing you to see areas that have burned in and around your site. This fire count is actually the fire count summary data that we publish with the fire dataset. And here's one of my favorite features. For more than a dozen different spatial datasets, we provide on-the-fly calculations specific to your polygon area, allowing you to learn things like elevation, precipitation, temperature, and vegetation for your site. For this site, we can see for those two polygons I drew that the average elevation is about 7,760 feet. The average maximum minimum temperatures are 56 and 32 degrees Fahrenheit respectively, and the area receives around 16 inches of precipitation in an average year. We have many more additional features, including allowing users to drill down into specific overlapping and nearby treatments, see details, learn about drought forecasts for the future, and learn what has happened in the area in the past. All this information can be exported into a report that can be referenced and shared. But what about the Wildland Fire Dataset? Well, we are currently working on finalizing our Wildland Fire Trends Tool, or WFTT. One thing you learn when working for the federal government, we do love our acronyms. The link on this page isn't active yet, but we plan to have this published and available to the public later this spring or summer. Like the Land Treatment Exploration Tool, the WFTT is designed specifically so that anyone, regardless of their knowledge or skill level, can learn more about wildland fires in the United States in an area of interest. Unfortunately, due to the sheer amount of data involved, because we're talking millions and millions of rows of data for just what we have now, this is also limited to the western contiguous US. However, we hope to be able to expand it in the future. So remember all those fire data sets out there? Depending on which one is used, if care isn't taken, incorrect or flat out wrong conclusions could be drawn. Even if it's used correctly, due to the differences in the fire data sets out there, their completeness and their time periods, scientists, the media, and the public can come to different conclusions on fires and fire trends, even if they do everything correctly. We need to provide something consistent that allows anyone to compare fires and fire trends in different areas across time and see the same results that a different person would. By using our fire data set, along with one other consistent data set for a more statistically valid fire trend mapping, we can ensure more consistent results for all users when analyzing fires. The tool has two main sections. The first and most user-friendly section for the public, which I'm showing here, allows users to select an area of interest and look at fires. You can select by state, vegetation types, fire types, land ownership, and several other categories, including the Wildland-Urban Interface, or WUI, which looks at wildland areas close to human populations. The WUI is a critical zone, as it should be our buffer to help protect populated areas from wildfires in wildlands. Currently, I have the data filtered to show all the fires in Idaho. The map on the left shows the full fire boundary for any fire that even touches the filtered data, in this case, our state of Idaho. As you can see, some boundaries spill into the surrounding states. The statistics, on the other hand, the total and area burned across the top, as well as the yearly and decadal counts on the right side, are for my filtered data only. In this case, just those parts of the fire inside the state of Idaho. So what can we do with this tool? Well, I can clear my filter and select different filter settings. Say I am interested in another region, something more specific like Rocky Mountain aspen vegetation, and a specific ecoregion like the Southern Rockies. Ecoregions can be thought of as areas of similar vegetation, soil, and climate types. So when I apply the filter, the maps and statistics are going to automatically change and zoom to the proper locations. I can hover over individual fires to get details like fire name and fire year. And I can look at specific statistics over here on the right, looking at counts of fire and hectares burned. And these are filtered by fire size. So we can see how the fires numbers and size are changing. We can also look at a more aggregate look of fire size by decades and see if that trend is going up or down. As I said before, we know our fire data is incomplete pre-1984 when satellites first started mapping fire boundaries, as not all the fire boundaries have been digitized. So if you really want to dive into some serious statistics with a more complete set of fire data, the second section of the WFTT allows you to look at scientifically valid fire trends from 1984 to present using the Monitoring Trends in Burn Severity Fire Dataset derived from satellite imagery. You can see whether the fire trend is going up, down, or staying level, whether that trend is significant, how much area within your selected area has burned, and how much of that has burned multiple times. In this example, I'm looking at wildfire trends in WUI and non-WUI areas of 4 states. There's a ton of detail and statistics here that I'm not going to go into, but by making this data public, we are allowing anyone, scientist, reporter, or interested member of the public to see the same data and come to the same conclusions. So let's wrap things up because I've been talking for far too long. So if you take anything away from this presentation, I hope it's these points. First, let's not make the same mistakes of the past. Many of you might have heard that our extreme fire suppression policies in the early 1900s led to overgrowth in understories and forests, and that has led to some of the severe forest fires we are now experiencing. I often wonder what mistakes we are making now that we will look back on and wonder why we did them. Let's learn from our past and present by making sure we record it properly. Second, long-term data sets are extremely powerful. They can teach us about our planet's history and how humans have changed over time. Third, context matters, and I come to this again and again. In this age of information and misinformation, it's important to understand the details behind the data. While it's easy to look at a figure and accept it as truth, I hope I've given you a glimpse today at how long-term data, if misused, can lead people to draw incorrect conclusions. Understanding the data, how it was collected, where it is strong and where it has issues is important in understanding the bigger picture of what the data is telling you. Finally, scientists all over the world are learning how to use interactive tools to make their work more engaging. Tools like the Land Treatment Exploration Tool and Wildland Fire Trends Tool are popping up everywhere right now, allowing people to explore and interact with data like never before. Take advantage of these tools to explore the world around you. It is truly a fascinating place. I have far too many co-authors and collaborators and funders to thank individually, and just want to say a big thank you to all of them here for all of your help and support over the years. Thanks for listening to me, and being a dad, I have to finish with a bad dad joke and ask if there are any burning questions anyone wants to ask. Thank you again.
Thank you, Justin. That was great. And I love the dad joke in there too. So yeah, a lot of great material covered. I mean, I'm in California myself, so I certainly understand the importance of having this kind of data available. So just so everyone knows, I've been keeping track of all the questions. So let me go through here. Just a reminder, if you guys have any burning questions you want to ask, go ahead and click on the Q&A chat window. It's that little question mark icon in the upper right. All right, so let me scroll up here, Justin, and get the first one. This one came in from Allison. Looks like she's with BLM. Allison says, I manage 20 years of treatment monitoring data from Central Oregon. How may I add this data set into your database? And she does provide an email that I can pass along.
Yeah, excellent question. And absolutely reach out to us. You can reach out to myself and I will put you in touch with the rest of the team as well. And I guess it depends on the kind of monitoring data that it is a little bit. If it's treatment-based monitoring data, we're going to associate it with the treatments. If it's other kinds of monitoring data, we'll work with you to try to provide that data as part of the land treatment exploration tool.
Okay, great. And Justin, I went ahead and Allison as well. I put your contact information in a reply to her, and that's obviously available for everyone else as well. It's to Justin's USGS staff profile with his contact info there. Okay, great. So the next one that came in, I actually took care of this. Someone asked if this talk will be available as a recording to view later and share with others who missed it. And just so everyone out there hears, yes, it will be available on our public lecture website. It'll take about a week for us to get it posted, but it'll be on there I'll give the public lecture website link at the end of the talk. Let's see, here's one that came in from Anonymous. They're asking, when you correct errors from other sources, do you communicate those errors back to the original provider so they can improve their data as well?
Yes, and that's another excellent question. We absolutely do that. And so errors are just a part of any big data set. There's just no way to get around them. And so, yeah, we're working really hard to communicate the errors back to the original data set provider so they can be corrected. And I'll give you a great example of that. Some of the fires in the fire data sets are perfect circles. And anyone who knows anything about wildfires knows fires don't burn in perfect circles. So what somebody did was they took a centroid point of the fire and buffered it by the area that was purported to have burned and turned it into a circle. And so we have flagged all of those circle fires, and we're working with the original agencies because some of those real fire polygons do exist. And we're trying to get them corrected not only in our own data set, but the original data sets as well.
Okay, great. It looks like we maybe have one or two more here. I think this one may have been covered. Does the USGS have long-term data sets like what you've shown for areas outside of the United States?
For some things we do, and for some things we don't. And so it's going to depend on the kind of data that you're interested in. We are the United States Geological Survey, so we are mostly focused on the US. But for some things, we do have long-term data sets for things outside the US as well. So it's going to depend on exactly what you're interested in looking for.
Okay, great, thank you. And it looks like this might be the last one here. A bit of a comment and a question. Anonymous says that 1910 fire was huge. Could something like that happen again?
You would think no, that it couldn't, because we have now a better communication, better ability to fight fires, and better ways of controlling them. But we do get many large out of control fires that are extremely dangerous and deadly and burn hundreds of thousands, if not millions of acres. And you can see that in places like California in particular, where we hear about these large fires burning through and destroying whole towns, unfortunately, and killing many people. And so maybe a 3 million acre fire isn't going to exist again, But, if we have an extremely severe drought in one year, as we often have, or, the entire West is in a drought right now. And so we're seeing some of those effects of these big fires. So I'm not going to say it's impossible. It could happen again at some point. It's just unlikely because we're better prepared to battle these large fires now.
One more did come in. This person says, living in an WUI area, we receive multiple wildland fire warnings from NWS. How can we better assess how alarmed to be when these alerts are issued?
It's a question that I'm not going to be good at answering. You should always take those fire warnings seriously, mostly because fire literally creates its own weather. So a big wildfire will create its own wind, will generate its own weather patterns, and can become extremely unpredictable and very difficult to control. And they give those warnings because there's a chance that it could burn into those areas. So I would say you always should take them seriously when they give you those warnings. And the reason we have the WUIs and they talk about those defensible zones is so that you can protect your house from the wildfires as best you can. So I'm definitely not an expert on WUIs or those fire warnings, but my recommendation would be to always take them seriously to protect yourself first and foremost, but also your property.
Absolutely. Good. Another question just came in. We go here. Addison asks, do you have any suggestions for people managing data at small research stations? What do you think are the most important things to keep in mind so data can be useful to multiple users?
It's another excellent question. And I think the important thing is to reach out to others, to see what others are collecting. And so this is something that we do for the Wildland Fire Dataset. You see, I have that huge group of fire advisors telling Michelle and I what's important. For the Land Treatment Digital Library and for the Conservation Efforts Database, which is another data set that I manage, we have focused user groups. Again, people who have a vested interest in this data telling us what's important and what we should be collecting. And, people like myself who do these kind of big data sets for a living often consult and work with other users to help build the databases, to help give you the different costs and benefits. And so again, it's something you can reach out, and we're happy to talk with you about things you want in a data set. There is no one right answer to that question. It depends on the type of data you're collecting, whether it's monitoring data or treatment data or another type of data. It depends on what's important to you and to that type of data. And so that's the best answer I can give.
That's a great answer. I don't see any more coming through, so I think that's going to do it. I'll give another second or two here, but Justin, a huge thank you to you for answering all these questions, for giving such a great lecture, something we're going to be able to archive on our public lecture website and have for many years here. So thank you, Justin. And just thank you to everyone else out there for joining us today. As I've mentioned a few times, in case you want to watch this again or share it with others, Justin's lecture will be available in about a week for on-demand viewing on our website, which should be shown on the screen here. The website is www.usgs.gov/PLS. You'll also find over 180 archived lectures on that site over the last 20 years that we've been holding this series. So make sure you check that out. On the website, you'll also find mention of our lecture schedule for the remainder of this year. We're fully booked and we have talks on topics ranging from volcanoes in Alaska to endangered bumblebees to our National Geologic Map database. So lots of good stuff coming up. As I mentioned in the beginning, if you want to be added to our mailing list, we only send 2 emails, one in the beginning of the month, one at the end. To get notifications on our lectures, just send us an email at wmcesic@usgs.gov, and we'll add you to our list. And finally, the flyer that was just showing there, that's the flyer for our lecture for next month. which again is May 26th at 6 p.m. Pacific time. And that will be Paul Young's talk on the use of remote sensing technologies to support science. So until then, thank you again, everyone, and Justin for joining us, and have a wonderful evening. Bye for now.
Thank you, everyone.